Good morning again on the West Coast, good afternoon on the East Coast, good evening in Europe and Asia. Welcome back to our second Xendee live walkthrough. Today we are dealing with advanced multi-node modeling analysis. So if you remember and if you participated on Monday, we were showing you how in principle Xendee is working in a single node version, but today we are going a little bit deeper, and we do it in a similar way like we did the last time. We have a couple of slides to set the background. I will do this, and then of course Rita is going to walk you through the model. We have also Giovanni here and Shamini, colleagues of ours. They will help answer questions if they're popping up in the chat window. And as already said on Monday, we had to change the structure, unfortunately, because there are so many people interested in this that we cannot really wait for everyone, and this is why we have this walkthrough. But as said, on Monday, we'll send you the credentials, the password, username after the conference, and of course the project, so that you can play around with this for 2 weeks. And of course, we will also walk you through challenges that you might face after the conference. Another thing that we haven't really well advertised during the conference, and we forgot about this on Monday and Tuesdays, that of course, as we said in our announcement, that you can win a platinum license for Xendee for a full year here, and depending on how many sessions you are joining, the chances will be increased to win this license. Just want to point this out because we never said this at the kickoff. So Rita will share the slides again. So Rita, next slide, please. So first of all, on a very high level, I will talk about what a multi-node model is, when we should use multi-node modeling, and what are the key features or components in a multi-node. And then I'll talk a little bit about a real powerful analysis and a one-line diagram, which we have in Xendee, but we're not going to debate this in this Xendee University Week because it's a little bit too much. And then there's, of course, the live walkthrough in Xendee Design through Rita. So next one. So what's a multi-node version model? I mean, you see this already on the right-hand side. It's really a distributed system. And you see in different colors here, different cables and lines. Basically, what we're doing is we have different nodes, interconnection. We have connection points for different loads, for different technologies, and so on. So we can really also model losses in the system and where to place technology. So it's really used for more detailed analysis as well. Losses in the system, voltage levels are considered. So it's basically the same techno-economic decision making that we were describing on Monday, but it's with a constraint on the cables and transformers. So if there's a bottleneck in the system because one cable couldn't handle it, then we notice, and of course we can either upgrade the system, the cables, transformers, or place the technologies at a different place. Next slide, please, Rita. So I was already talking about this a little bit. I mean, single node is really, you aggregate everything into one node, and you have seen this on Monday. So if you have multiple nodes, you have to aggregate them. We can have multiple technologies, but they're all connected at one node, and there's no real energy or power flow between the different technologies modeled, like in terms of losses. And in multi-node, we distribute this, and this actually gives us higher fidelity here. And it's not only electricity, it can also consider heating and cooling pipes. Next slide, please, Rita. Okay. So, I mean, I think it's pretty clear when we want to use multi-node modeling. It's really when we have larger systems, more distributed, maybe different load voltage levels in the system that we want to model, or even critical loads that we want to serve in terms of outages. And the thing is, typically our clients, or we, when we use the software for our engineering work, we start with a single node, right? Because you want to get the system right, you want to see what's going on, and you want to get a high level view. And then if you want to go deeper, or have to go deeper because you're not only doing screening and you go into detailed engineering, then you would use the multi-node version. And in Xendee, you can directly go from a single node into the multi-node with the click of a button. And then actually do all these analyses. And then actually, when you're done in multi-node, and I will show you this later, we can go into single line diagram and do more detailed analyses. But today we are really focusing on this multi-node. Okay, next slide, Ria. The benefits, I think, are pretty clear here. I mean, we have higher fidelity. We can also consider real scenarios like, I mean, bottlenecks, transformer capacities, and all this stuff, and even voltage levels. One thing I should note here is this is a hybrid between a power flow analysis and an economic optimization, in the sense that the time steps are not going down to milliseconds or seconds like you would expect this in a one-line diagram or a power flow analysis. Here it's really more to get a high-level view of the distribution system, and this means we can go down to 15 minutes, and everything which is happening between 15 minutes is not captured, but it's a good starting point to actually consider the topology and the distribution system and see how this might impact the placing of technologies or the losses, because someone has, or some generation technology or the utility has to provide these losses. So this is all what we can do here. And then, of course, we do still a cost minimization like we do it in a single node. We're trying to size the technologies, but just with this additional information. There are different ways of considering the cables or pipes. I mean, we can specify this, and Rita will show you this. I mean, X over R ratios and all this stuff, but you could also use this in a way that Xendee is designing the underlying cables and transformers for you at the same time when it's considering the technologies, the DRs. Next slide. One thing I forgot to mention is we're doing this the same way like on Monday. So if you have questions, we will screen them in the background. So if you feel you want to ask something which is important for you, then, or for the team here, then just let us know and we will try to answer them while we go for the whole demo here. In terms of components for the multi-node modeling, I mean, also very straightforward. We have these nodes, and these nodes are just connection points where we can connect electric loads, thermal loads, cooling loads, distributed energy resources, like you have seen this in the single node, but just more distributed. So in this way, we could create systems where we place renewable energy just on a certain feeder, and the nodes are somewhere else, right? So we can model all this. Transformers are part of this because we now have different voltage levels in the system, so we can model this, and of course, cables and pipes. Next slide, please. Individual loads. So this is one thing. So now you can separate the loads. I mean, you could have a community, and I think on Monday, as I was walking you through the slides here, I was showing you the University of California, San Diego as a multi-node version where we did a project with the university, and there were all these individual loads, all these different technologies distributed all over the place so that we could model this. And another thing is we have also some movies, and I think later on we have also a link to the Xendee University or YouTube channel where you can actually get way more details about the background on the multi-node modeling, which we are not touching on today because it might be too much. So I think one thing I forgot is also we have district heating and cooling, which was something which maybe you were watching the European sessions today, but district heating is something which is very popular in Europe, and this is why we also have these capabilities to do district heating modeling in a distributed way. Next slide, please, Rita. Okay, next one. So you will see this also in the tool, but basically, when we say powerful analysis, we are looking into what is the capacity of the lines, cables, transformers, so the branch capacities, And because of the parameters that we're considering, X over R, we can also calculate voltage levels and losses. And that's what you see on the right-hand side. So we are capable now of calculating active power and reactive power and how it is flowing in the system and what losses we have and so on. As I said early on, this is a high-level combination of techno-economics with the power flow. So it's not really in the milliseconds, but for the design of the system from a thermal perspective, this is sufficient. And then later on, we move this anyway into the one-line diagram and can do a quasi-static analysis or a snapshot analysis for certain scenarios. When you run the power flow in Xendee, you have multiple options. So the first option is you run the topology without any power flow. So you're just modeling a distributed system, but you, in a simple case, you're not concerned about the cables, transformers, the capacitors, the branch capacitors, the voltages. Sometimes we do this to just figure out how the energy would flow, and then we restrict it with branch capacitors. We can turn this on and off, and then also maybe voltage levels and so on. So the different features on what level you can achieve within Xendee when it comes to this model. Let me just see a couple of questions. I'm not sure if I understand this question. Any functions to insert the R value of the building envelope to get an accurate reading of how this system will need to operate? I think this goes a little bit back to the demand. So we are not implicitly modeling the demand, heating demand here. So this is really loads are given in terms of kilowatt hours, right? So my best read of this question is that no, we're not doing that. Okay, next slide, Rita. So I'm not going into the details, but we are basically using a linearized distribution flow, a lin-dist flow for the power flow calculation. So it's linearized. We assume it's also three-phased, three-phase balanced system for the first analysis. In the one-line diagram, we could do unbalanced systems, but I mean, just for designing the system, we are using here balanced systems. By the way, here's also the link to the YouTube channel. And Rita is doing a lot of engineering movies to help our modelers or you to better understand what's going on or giving them tips. And there's also way more information on the power flow, other topics around multi-node financing and so on. So if you want, just go to that YouTube channel and check out the short movies, 5, 6, 7 minutes, which have more details on it. Next slide, Aria. So, and this is the next step that I was mentioning. This is where we go now from this techno-economic optimization, where we decide where to place PV batteries, generators, into one line diagram, which is needed for more sophisticated studies later on. And with the click of a button, we transfer this over and can do then quasi-static analysis for a full year, which we are releasing just, I think, this week or next week, or snapshot analysis, right? So very detailed. This could be also the starting point for transient analysis. And I think I mentioned this on Monday in the intro session that we are not providing transient analysis capabilities in the software because it's just such a specialized field that we feel that this needs to be done in-house or by a very specialized expert. Okay, so one line diagram. I think you see here on the right-hand side, I mean, in this picture, there's a button, which is, I mean, you don't see it really well now, but we will see later on in the demo, there's an open one line. So we go then from the multi-node in the one line, and I already told you, I mean, we can do snapshot and quasi-static analysis. So I think that's pretty much it. That all about what I want to talk about in terms of background readers. So no, well, here's the YouTube channel again. just so that you can check it out. And it's really sorted around the capabilities, and there's one multi-node modeling basics, which we added and so on. So you can find way more there. So Rita, I think with this, we go now into the walkthrough. And by the way, we can have also conversations about things that we discussed on Monday, because I think we have today more time than on Monday. So if you feel that there's still something unanswered from Monday, we can also have conversations around this. And Shamini or Giovanni can also help in the background with the Q&A. But with this, I want to hand it over to Rita. Thank you.
Thanks, Michael. I'm going to take a moment to switch my tabs. Do you want to answer the question about Q&A while I do that?
Is the question is there feasibility, and let me just turn it on, is there feasibility analysis after the Lindy's power flow analysis? So I'm not fully sure if I understand that question, but I think what it might mean is, of course, there's some iterations, right? I mean, you start with Xendee single node, you do a multi-node, you maybe go then into the one-line diagram, into the original part, because maybe you discover something in the one-line diagram which needs a change in the power flow model in the multi-node that we are discussing today. So my answer to this is yes, there's a loop in practical terms where you go back and forth between the different features in Xendee, but that's exactly the reason why we have an integrated platform, because we don't want to have that you constantly have to export or input stuff to other tools, because this is slowing you down, creates issues, and this is why this is all linked in one platform where you can go back and forth to some extent.
Okay, great. Thank you. So now we're going to move on to the live walkthrough portion of this session. And I think some of you joined a little bit later. So in case you missed it, because we've gotten such an overwhelming demand for the live training sessions, we're actually going to walk through the sessions in the live sessions as is. For the free trial, the 2-week trial, we will send you the login information as well as the recordings and the presentations, of course, after the conclusion of this conference. So that's the conclusion of Xendee University Week. So we hope to get you all that information around early next week. So don't worry if you haven't seen any information about your logins for the free trial. We haven't sent that out yet. So just stay tuned for that. And for this session, what we're going to do is basically a walkthrough of how to convert a single node model into a detailed multi-node one. Now, if you were in the session with us on Monday, then you know that we went through a simple data center Xendee model. However, in that model, which is shown on the screen right here, we're assuming that everything is aggregated in basically one point of connection, which is probably not realistic for data center projects. You know, you're probably going to have like a district cooling system. You're going to have DERs connected at different points. So what we're going to do today is actually advance this model from a single node version into a detailed multi-node one, and that'll be more realistic to what you might actually see when you consider power flow, losses, and connections. Again, if you have any questions about, what I did, like if you missed a step or just about general questions, feel free to drop it in the Q&A section of Zoom. If you don't see the Q&A button, you might have to click on more in the little 3-dot symbol at the bottom of the Zoom window. And once the questions come in, my colleagues, Michael, Shamini, and Giovanni, we're all experts in PowerFlow and Xendee. They can take the time to either type in answers or we'll answer them live as we have time at the end. But for now, let's get into the model. So this is my single node data center model from Monday. As you can see, if we zoom out here a little bit, this is kind of what it looks like. So very typical data center. The first thing we're going to have to do is actually change this from single node mode into multi-node mode. And at the top, we can do that seamlessly from our settings window. Now, I am going to be skipping over a lot of the fundamentals of setting up a microgrid project in Xendee. So if you've never seen Xendee or you were in the Monday session before, just know that we are skipping over a lot of the very basics of setting up a project just because we're kind of more focused on multi-node today. But one of the options I'm going to have is actually convert this into a multi-node project. And what that's going to do is give me additional symbols as well as capabilities for power flow. So I'm going to go ahead and enable that. And once you do this, you're going to see at the bottom where our symbols bar live is in addition to all of our DER selections, we're also going to now get symbols for connections, so such as cables, transformers, our thermal connections, and of course, additional nodes and buildings. And this is what's going to allow us to actually assign individual building loads to their respective locations and nodes. Okay, so the first thing I'm going to have to do is actually delete all of these symbols because I'm actually going to assign them to their respective locations. So just bear with me while I pretty much get rid of all of these. But this will kind of give you a preview of what to expect as we transition into a more detailed model. Is we're going to have different building loads as well as all of these DRs, but placed at their respective kind of locations on our site. So now we have a blank slate here of our data center. Let me zoom out so you can kind of see where it is. And remember, in multi-node, your losses as well as your DER placements are going to actually play into your optimization depending on your connections. So I am going to try my best to kind of model this in a realistic manner, but your data center site might look different or your connections might look different. But for this one, I am just going to go with what I think is going to be somewhat realistic. So first, we still have our utility connection. This is what we're going to be assuming to be our connection for utility power. So let's open this up first because I'm actually going to change the voltage on this one. So under this power flow tab here, you'll see we can actually set the voltage at the utility connection. For this one, I'm actually going to bump this up for the utility connection just because we're going to be drawing a lot of power. And then what we're going to do is for the nodes that will actually serve our electrical loads on site, we're going to progressively step down so that it's more appropriate for our data center site. So I've set it up to 34.5 kilovolts here. For these, I am just going to leave as the default. Okay, so now that we have set our utility voltage, what I'm going to do next is actually add and define all of my nodes. Now, you remember earlier from the presentation, a node is basically a point of electrical connection or thermal connection. And what we're going to do is add a few of these on our site. So from the bottom, the symbols bar here, I'm going to click on the node symbol. So you can see it says node or junction point. So for the first one I'm going to add is what I'm going to call my medium voltage switchgear, which is going to be basically my next point of step down from the voltage and what I'm going to be distributing to the rest of the system. Now, you can't add costs for installation or maintenance cost if it's going to be a brand new interconnection, which, as we all know, is going to be usually pretty expensive for a data center. So you can add those costs in if you like. But for now, I'm just going to leave all the costs for the nodes as blank. So let's just say my, my medium voltage switchgear connection is going to be like right here, maybe this little like electrical part right here. Now the next node I'm going to add, which we're going to have to step down again as far as voltage, is actually where my on-site generation as well as consumption is going to be. So let's first add a kind of a feeder node for our cooling stack. We are going to assume to have kind of like a dedicated cooling stack on our data center. So which we'll do later is actually add a electric chiller to this cooling stack. But that's going to be where it is. And now I'm going to add a node for our, what I'm going to call like the admin offices. So I will have to attach a load to this to represent the admin portion of our data center. So this could be like, the office or like the lunch break room or like where your 5 data center employees actually like work. So let's assume that feeder for the admin is. Now I am going to add a kind of intermediate connection that I'm going to call an uninterruptible power supply. So let's assume this is like kind of where the like electrical room for your actual server racks is. So like maybe this is where you have the battery. Maybe this is like where they like scrub the power before they actually feed into the server racks. So I'm going to put it here. Let's assume this is like our little server rack space. And then the last node I'm going to add is actually the feeder for the server hall or the server racks. And let's assume like the server racks is around here. And all these symbols, you can always drag and reposition them if you didn't like where they are before. Now we have all of our nodes, and the next thing we're gonna have to do is actually step down our voltage, because remember, currently we've set our voltage starting point as basically what it is on the utility. We're not gonna be able to use that at our data center, so we need to first step it down. So let's first step it down to what we are gonna have at the medium voltage switchgear. So from the bottom at the symbols top bar here, I'm now gonna add a 3-phase transformer. And once you click on that, you're going to see it's going to ask you to select the nodes that you want to connect with your transformer. So my primary node is going to be my utility connection, which is what I'm stepping down from. And then my secondary node is going to be my medium voltage switchgear, which is going to be my first step down. Go ahead and add the transformer. At the top here, you'll see the connection as well as the voltages. So the primary side voltage is already filled in because this is what we set at the utility connection. So now I have to fill in the secondary side voltage, which I'm going to assume to be 13.8 kilovolts. But don't worry, we're going to step this down again when we actually get closer to our admin room. So for the transformers, there's several options as to how you want to fill in your investment as well as power flow specifications, because these, especially the power flow inputs, are going to affect your power flow losses as well as outputs and optimization. So the first thing you can always do, and you can always do this for basically on any of the inputs in Xendee, is that you always have the option to just manually input the numbers yourself. So if you already have a model or a manufacturer in mind, you can always do that. The second option is using our global catalog. So we have a pretty extensive catalog of some manufacturers, as well as just some like usually industry standard models. So you can browse through here and pick out an appropriate transformer that way if you like. The last option is what we call Xendee sizing. So if you turn this toggle on, what this is going to do, and this is what the yellow label right here will say, is that Xendee will go through the catalog and select a transformer for you that both minimizes the cost and is going to do so while making sure that it's subject to the capacity, voltage, and power flow constraints of your optimization. So that's what I'm actually going to do for this transformer right here, is I'm going to use Xendee sizing. And then we'll see in a little bit in our report exactly, what transformer Xendee has selected for us. Now I'm going to click save at the bottom left. And now you'll see, let me zoom in. Now we have a little transformer connection symbol between our utility connection and our medium voltage switchgear. Now we have a few more voltage step downs that we have to do. So now let's step down from our medium voltage to both our feeder for the cooling stack and the feeder for our admin room / office. So again, from the symbols bar here, I'm going to add a 3-phase transformer. This time I'm going to now pick from the medium voltage switchgear to our feeder for the cooling stack. So now at the top here, you'll see now our primary side voltage now reflects the voltage of the medium voltage switchgear. For the secondary side, I'm going to bump it all the way down to 480 volts so that we can use it at our actual point of generation and consumption. Again, for the actual transformer, I am going to use Xendee sizing and let Xendee pick one for me. And we'll see this a little bit in the optimization result. You'll see that Xendee will actually pick a smaller transformer for this specific connection due to the smaller voltages. So let me go ahead and save that. And I'm going to repeat this process for the admin / office. So again, we're dropping down from the medium voltage switchgear to our admin. Same thing as the cooling stack. I'm going to assume just 480 volts, and I'm going to use Xendee sizing. Okay, so now we have basically connected our utility to our right-hand side of our site here, which is our cooling stack and admin room. As we go over to our server rack side, this is going to be a little bit more complex because instead of stepping straight down, I'm going to first connect a cable from our medium voltage switchgear to our UPS room, and then we're going to drop down the voltage again to the feeder when it's actually closer to the point of use. So let's now add a cable. So from the bottom at the symbols bar, I'm now going to click on the cable connection. Now, again, it's going to ask you to pick the nodes that you want to connect. And the cables in Xendee are assumed to be bidirectional, so we're going to be able to send power back and forth. So let's connect our medium voltage switchgear and then our uninterruptible power supply room. And once you add this cable, you'll see at the top, it's going to look slightly different. You're going to notice that the cable is going to have a line length, and this is also going to play into optimization because the length itself is going to play into both your cost as well as your losses. Now, you'll see that Xendee has automatically calculated 265 feet, and that's just purely based on the placement of the nodes that I have put on the model.
Rita, just since you said feet here, just for our friends from other parts of the world, this of course is completely internationalized, and we could have switched to SI units, but here we are doing imperial units, but this could be meters, this could be something else. Just pointing this out again.
Mm-hmm. Yeah. Perfect. And you also do not have to use the Xendee kind of auto-calculated length. If you have like already figured out the length of your cable, you can also override this and input that yourself. Now you'll notice the voltage here is 13.8 kilovolts because remember, that's what I have currently dropped down to at our medium voltage switchgear. Now for cables, again, you have several ways of actually inputting your investment and power flow specifications. First one is you can always input your own values. And this is what I'm actually going to do for this part is I'm going to input in my own values. Now, it's really important that you enter in power flow values that are going to be appropriate for your connection and your site. Because, for example, if you entered in like an ampacity that's way too low, you're going to end up getting what we call an infeasible solution or infeasibility. And that's going to be due to not being able to transfer enough electricity between your from your cables. So I'm going to enter in my own specifications here. Now, actually, once you do this, and this is also true for any DER or connection type in Xendee, is if you input in your own custom values, you can always actually save it to your own like personal catalog or team catalog. So if the future you want to pull up the same cable or DER again, you can just do that very quickly from your catalog. Also for cables, we are also going to have a Xendee catalog, and this is going to have a lot of, common manufacturers, and you can see you can or browse by like size, rating, ampacity, material. The last option you also have is Xendee sizing. So if you select this, Xendee is also gonna pick a cable for you from our catalog with respect to both of your optimization objective as well as your power flow constraints. But for this one, I've inputted in my own specs, and I'm gonna click save. And now you'll see on the map here, we now have a cable connection. But what's special about the cable is that you can actually drag the little connection dots to kind of map it out more realistically. So if your cable is like really winding or really wraps around your project, you can do that. And as you do this and change your cable length, you'll see that if you click back on it and go look at your calculated cable length, it's going to automatically update just based on the location estimates. Okay, I'm going to change this back to my previous layout. Okay, so now we have a cable between our medium voltage switchgear and uninterruptible power supply. Now, the last step that I need to do is between my UPS to my actual feeder for my server racks. So let's go ahead and add that last transformer. Again, I am going to step this down all the way to 480 volts, and I'm going to use Xendee sizing. Okay, so now let me zoom back out. We've basically set the skeleton for our distributed energy as well as district cooling system. If your site has more nodes or more rooms, or if you want to really make the connections even more detailed, of course, you can add more cables and nodes. But for this one, I think it's going to be pretty good for our walkthrough today. So now I'm going to add my building loads. So remember that in single node, we had basically aggregated all of our nodes into one singular load for our entire site. Now, for a lot of sites, or maybe just like feasibility studies, it's totally okay to just aggregate all of your loads into the one site. But now that we have our connections for power flow included in, we're going to separate our building loads into their respective locations. So I'm going to have two nodes or two building loads in this case. I'm going to have my office/admin load, and then I'm going to have my actual load for the servers. So from the bottom here at the symbols bar, we can now add individual building loads. And you'll see that you have to assign it to a specific node because, it has to be tied to a point of connection. That's also how, how Xendee will calculate the losses. So let's first start with our admin load. And if you were in our Monday session or any of our previous Xendee sessions, you know that we have multiple ways of adding in a building load for your site, as well as a catalog or your internal catalog. For this building load, the first way I'm going to add it is actually with the NREL load shape tool. This is a great tool if you don't have like a historical time series or interval data file for your site. So our data centers in San Francisco. So I'm selecting San Francisco. I'm going to assume this to be pretty akin to like a medium office. That's new. And for the NREL load shape tool here, you basically just have to enter in like what you think the annual consumption as well as the peak demand is going to be. So I'm going to input in consumption and peak demand values here. And we're going to do this for both electricity as well as cooling. We're not going to have any heating, so I'm just going to ignore the natural gas part. So now you can see on the right-hand side, the NREL load shape tool has generated for us like a typical medium office demand profile based on the consumption and demand values that I've input. So we're going to input or import the electricity only load profile. As you can see here, during the daytime, it's going to go up, probably because that's when the people are working, coming in. And then evening and early morning, there's going to be basically very little demand. We're going to have our cooling. This is going to be, again, typical for a medium office. And you can also see that it changes seasonally. September, August, summer months, it's going to be a lot higher, probably just for, running the AC. So now I'm going to import these load shapes into my model. I'm only going to do electricity and cooling, so I'm going to deselect the rest and then import these load shapes. So now that you see here, we have our electricity as well as cooling profile for just our office. Going to save, and once you do that, you'll see now I have a little load icon attached to my feeder/admin. And I can also drag this around, but it actually doesn't matter where I drag the actual load icon to be because its location is tied to this feeder. If you want to put this farther away and still have that connection or the cable length to count, you can just add another node. So we have our load for our admin. So now let's add our load for our actual server hall. So again, from the bottom here, I'm going to add another building load icon. And I'm going to assign it to our server hall feeder this time. And for this one, I'm actually going to enter my own load shapes. So if you have, complete CSV files of your load data, you can also just directly upload it. You have to pick the load shape start date, as well as a time step. So we accept our 30-minute or 15-minute interval data. Mine's going to be 1 hour. And then you also have to select what type of load you're uploading. In Xendee, we can accept up to all of these. For this model, we are just going to be working with electricity and cooling. So I'm going to upload my electricity only load first. So I'm going to go ahead and upload that, and you'll see it's now pulled in my data file. And just to note here, our load for this data center is going to basically vary between like 6 megawatts to about 13 megawatts. And now I'm going to enter my cooling load shape. So when I say my cooling load, I am purely just talking about the electricity that's going to be, the cooling that's not connected to, that's separated from the electricity use. So if you have an electric chiller and electrical demand because of that, you have to either make sure that you separate it out to its own cooling demand, or you can keep it as part of your electricity only load, but then just make sure that you're not also creating a separate cooling load for that. So just make sure you're not like double counting consumption as a result of cooling or heating devices that rely on electricity.
And let me add something here, Rita, because what Rita is saying is actually a point that we didn't really emphasize on Monday. I mean, you don't want to mix the cooling profile with the electricity profile because it reduces your flexibility in the system. And this is why we split this. I mean, you don't have to do it, but if you have the data, maybe you're metering the node in reality, which has the electric chiller, then you know your electric demand for the chiller. And if you have this separated, you have more options in terms of the optimization, because later on, when you optimize the system, you could go from absorption chiller using some waste heat from a generator to do that cooling, right? So if you lump everything together on the electricity side, then it's not a very smart way to do it because you're reducing the possibilities for you. And this is why we have this differentiation between cooling, heating, and electricity, right? And this is what Rita was pointing out.
Yeah. Great point. And we'll actually see in this model how we're going to transition from relying on purely electric chiller to absorption chiller in this case. So that's why I have the cooling load separated out in this case, because it's also going to drive a lot of our economics as well as potential for saving. But now that you see we have both of our load up here, we can see there's two tabs now. I have one tab that shows me the preview of our electricity load shape. And then I also have a tab for cooling, which as you can see, is going to be pretty similar to our electricity load shape, but on a lower scale. For cooling, we're looking at about like 1.5 to 4 megawatt therms. Now I'm going to go ahead and save this. And now you'll see I have a load connected to my server hall. Okay, so now that we have our base model defined with all of our connection framework and the load, let's go ahead and add our DERs. So the first thing I'm going to add is actually our existing electric chiller. This is what we're assuming our kind of base case or reference to be, is just running our data center purely on utility purchases and running a really big electric chiller stack. So for every DER that you're going to add, you're also going to have to select a node to add this technology to. Now, this is my electric chiller, so I'm going to add it to my cooling feeder. And for every DER, just as a quick review, in case you didn't attend our session on Monday, for every DER, you always have to tell Xendee a technology decision. And this basically what this is how you're going to tell Xendee to account for this DER in your optimization. So consider which we will use for the other DERs is it's going to be a potential new investment, but you don't know if it's a good investment and you don't know what capacities to set. For existing, this would be if you have existing technologies that's already on site or already purchased, so that you're not going to be spending new investment capex at year one. But if it does expire or retire before the end of your project length, you will have to replace it. So this is what I'm going to do for my existing chiller. Let's say we have a 7 megawatt chiller. That's 1 year old. And for the investment specs and technical specifications, I am just going to leave as the default values, but of course, feel free to change it if you have the exact model or specs. So I'll go ahead and save that, and you'll see now we have our electric chiller. Actually, I'm going to go ahead and change the name to existing electric chiller, just so we know we already have that on site. But you'll now see that it's connected to my cooling feeder here. And remember that we're working with a cooling load. And what this means is that we actually have to connect it to the rest of our nodes with cooling pipes so the cooling can be delivered. So at the bottom from the symbols bar here, I'm now going to select cooling pipe. And we are going to have to add this between basically every connection that will deliver the cooling. So first, I am going to connect it between the switchgear and the cooling feeder, because that is the next point of connection. And we can go ahead and add our cooling pipe. And I am going to just enter in my own investment specifications. And you do have to define a proper capacity as well as loss coefficient. Now, if you input a capacity that's going to be way too small for the amount of cooling that you're delivering, then you are again going to get an infeasible result. So make sure that these values are going to be appropriate for your site. So go ahead and save that. And what's now added to our site is this little blue connection you see here between the two nodes that we've decided to connect it with. So we actually need to deliver our cooling to both of our admin office and to our server hall. So I'm going to do that very quickly. Just bear with me. Okay, so now we have a cooling pipe between these two nodes. And then I'll add one last one directly to the server rack. Okay, and of course you can adjust your cables if you want to, make the layout like more pretty or exact. Okay, but now we basically have our district cooling for our base case setup.
Rita, let me just answer a couple of questions here. Since you mentioned saving, one question is if the system does have auto saving. Absolutely yes. It's just a habit that probably Rita has, like I have to save this manually, but it's saving this automatically. So there's auto saving. Vince, your question, why you're going through the switchgear rather than directly, I think this is just a modeling. This is just the assumptions that we take. This has no real meaning. So,
yeah. Yeah, I guess you can totally go straight from the feeder to feeder if you want.
Okay.
Okay, great. So now we have our cooling setup. The next thing I'm going to now add is our new DERs. So remember, we're going to propose the investment or addition of new DERs. Now, for reality, you're probably going to have to do this for the sake of like speed to power and not buying a ton of electricity from the utility. So that's what I'm going to do. So the first thing I'm going to add is solar. But we're going to be adding several DERs here just so we can kind of see a mix of different DERs. First thing I'm going to add is solar. So I'm going to add it to my switchgear. Now for the solar, you're going to see again at the top, you have to define the technology decision to tell Xendee how to account for this specific DER. Again, this is going to be a new potential investment, and I don't know if it's going to be a good investment or how much. So I'm going to click consider. So Xendee is going to solve for me if it's a good idea, and if so, how much. Again, you should always input your investment specs to the best of your ability because this is going to go into your cash flow, which is going to drive the techno-economic analysis. But for this exercise, I am just going to leave all of the costs as default. Now I am going to define a maximum install space. Let's just pretend, we only have so much parking lot space we can work with. So this is going to be actually a limiter on how much PV we can install at this site. If you scroll down, you'll see you have several ways of inputting your PV performance data. First way is you can always upload your own performance data. This is especially useful if you use a third-party solar design specific software like Helioscope or PVSys. If not, you can actually use our little integrated solar performance calculator here. And this is driven by PV Watts, which is also from NREL. So you can input in like your panel efficiency, specs. And what that will do is compute for you a solar performance for your site. So I'm going to leave the rest as default and save my solar. Again, you'll see now we have a little solar symbol, which I'm just going to place here so you can see. The next thing I'm going to add is actually some CHP or cogeneration gas generators. So from the bottom of the symbols bar, I'm going to click on gas generator because it is going to be a type of gas generator. But we also have other generator types, such as diesel generator and linear generator, also gas turbines, if you want to model with those. I'm also going to add this to my switchgear. Again, I am going to assume that this is a new potential investment. So for the technology decision, I'm also going to let Xendee decide for me how many, if any, is optimal. And I'm going to limit the maximum number to 10. Let's just say we have limited space for like a generator yard. For this one, I'm actually going to pull something from my catalog. So I'm just going to show you one other way you can pull your DER is if your project team or like your own personal catalog, you already have some models saved, you can just pull that from here. So now I've just pulled in a previous model that I've saved for myself. For the generator, for this specific case, I do want it to be a combined heat and power generator. And what that's going to do is it's going to produce electricity, which we're going to use for our site. But in addition to that, we're going to use our waste heat with an absorption chiller so we can actually use that waste heat into cooling. Now, if you have a heating load on your site, you can also just directly use that waste heat for heating. But we don't have a heating load, we have a cooling load. So we're gonna use that in conjunction with the absorption chiller. When you do that, when you enable the combined heat and power capability, you're gonna see a few extra specs pop up for CHP specifics, but I'm just gonna leave that as a default. But feel free to play around with this in your trial because CHP is a really great method to reduce both costs and emissions in some cases. The rest I'm going to leave as default. And I'll save that. And now you'll see we have our gas generator or CHP generator all tied up here. Now I've just assumed everything is connected to the switchgear, but if your gas generator is like gonna be in a generator yard like out here, you can of course like add another node for your generator yard and set the connections that way. Okay, the next thing I'm going to add is an absorption chiller because remember, we're going to use the waste heat from our CHP generator for absorption chilling. So from the bottom here, I'm going to click on absorption chiller. Again, adding it to my switchgear, I'm just going to assume that is co-located with my CHP. Again, I'm going to set this as consider and let Xendee decide for me how much, if any, to add. So now we have our cogeneration set here. So this is going to be kind of the main basis of our DERs. The one last thing I'm going to add is actually a battery to our uninterruptible power supply room. Now the battery, and we'll run a second scenario, but you'll see the battery might only come into case if there is an outage requirement. So let's just set this battery up first to see if we even need it in a regular case. So from the symbols bar, I'm now going to add a battery storage to my UPS room. Again, I'm just going to leave everything as a default for now and let Xendee decide for me capacity. So now we have a battery in our connected to our UPS room. Okay, so we've basically set up everything for our multi-node version of this data center. So just a quick recap of what we did. We basically now are really capturing the power flow as well as losses, basically all the way from the point of utility connection, all the way down to when you're actually using your utility purchases at your loads. So we've stepped down the voltage. That's what these.
So there's a good question, I think, Rita, which we want to also answer. Can multi-node be used without grid connection? And absolutely. I mean, it's we just modeled this with a grid connection, but it can be done without a grid connection. The only thing here is, of course, you should keep in mind that we're doing this down to a 50-minute basis. So you need to probably do a couple of iterations in this design mode to have enough capacity if there would be a bottleneck in the system. So because here we can always use the grid, but if you don't have a grid connection, then you have to probably also go into the one-line diagram and see if you have enough capacity to serve your loads on a smaller time step. But it's easily possible.
Yeah, and let me just show very quickly how you can toggle between a grid-connected model and a islanded or off-grid model. So from the symbols, or not symbols, the main bar at the top, you can go into the settings page for your model. And next to your multi-node toggle, there's also a grid connected model. So if you change this to no, it'll change this to a completely islanded model. So it's going to take away your utility connection as well as tariff rates. So I'll just show it very quickly because I can easily switch this back. So what that's going to do is now instead of a utility connection icon, we have a islanded connection icon. And it's really important in an islanded case to make sure that you have enough on-site DERs or generation sources, as well as fuels if you have fuel-fired technologies, to be able to serve the load that you define, because otherwise you're going to run into an infeasible solution. Okay, now let me change this back. So we're grid connected again. Okay. All right, quick summary of what we did. We now have a kind of a complete detailed multi-node model. We stepped down our voltage all the way from the utility to our switchgear to our endpoints used. And we also separated out where all the DERs and loads are going to be. So instead of being assumed to be all at the same connection and same node, all the DERs and loads are now at their respective locations, and they're going to be connected by either cables or transformers. For the heating, or not the heating, the cooling component, we utilize cooling pipes to deliver the cooling. But of course, if you have heating, you can also add heating pipes. Now let's go ahead and run an optimization and see what it looks like. So from the main menu at the top, we're going to go to the optimize window, and this is where we're going to run an optimization. And optimization is just what we call an analysis in Xendee, because Xendee is going to figure out for us the best capacities of DERs as well as the dispatch. So that's why we call it an optimization, because Xendee is going to find the best solution according to our goals. So let's just call this reduce cost run, because what I'm going to do is I'm going to ask Xendee to find me a reduced cost optimization. So it's going to find me the cheapest solution overall. Now, if your objective is reduce CO2,
Rita, we should. I just got a question here that I saw from Vince on how will Xendee determine battery size without additional info, for example, on load and duration. So maybe we should explain a little bit how the optimization works. I'm not sure if we thought if we did discuss this in detail enough on Monday, but I think first of all, yes, of course you have to define the load, and this is what Rita did. And if you're referring to duration in terms of how much capacity, maybe Rita, you want to go to the battery settings, and we specify battery. So as I tried to say on Monday, when it comes to optimization, we are not determining by rules how big the battery should be or how the operation should look like. We are just providing input data, right? So we basically provide the electricity loads on the different nodes in this case, and also the parameters of the battery. And there's, for example, for the battery that Rita is showing at the moment, there's a maximum charging rate, discharging rate. So in other words, this is for some people, a 4-hour battery that we have here, and then how it is scheduled and how big it will be then depends on the optimization. And sorry if someone missed, so it's no problem if someone missed at the part of Monday. We have enough time today to explain this, but it's basically figuring out how big the battery should be and how it should be operated within these constraints that we're defining based on load and parameters. Yeah. So there's another question: does the multi-node model optimize the loads rather than the supply side DRs and other sources? So it does both, and I know it's sometimes hard to figure that out if you're not too familiar with optimization, but the optimization tries to solve all these problems together, and this is why we're getting millions of combinations, as I was pointing out on Monday, where it combines a certain battery size with a certain other technology and operational level. So I'm not sure if you have realized this on the results screen. And Rita can show this again, there's the number of equations that we're solving, right? And it can be a lot of combinations. So we are solving the problem of what technology combination is needed and how we should run them. And we are not giving a preference to a certain technology or to whatever it is. It's really determined just based on the costs, the parameters that we're providing, electricity rates and loads.
Yeah.
Another question, maybe we stay on this. Is there a way to model, let me just take this away. Is there a way to model shifting overnight load to daytime, for example, for EV charging? Yes, I think, Rita, we haven't really discussed this, or maybe we did, and I cannot remember how electric vehicle charging and fleet charging can work, but that's possible here, and we can show this also later on if you like.
Yeah, we can maybe jump into EV charging if we have time at the end. Okay. I can also just answer this question about battery since I'm on the battery screen already. So I kind of flew over this, but for the battery text specification, you'll see it's a lot more specific to batteries. And you also see that with the different DERs in Xendee, the technical specs are going to change depending on the DER. So it doesn't have to be a specific type of battery. When we say battery energy storage system, you can kind of define it to whatever type of battery you're using. So it can be, lithium, sodium, whatever type of battery. The most important part, as far as inputs for Xendee, is, defining its charging efficiencies, C rate, state of charge constraints, module size, because this is going to be the part that's kind of go into generating and optimizing the dispatch as well as losses for the battery. And as far as evaluating multiple battery technologies, yes, you can do this. You would essentially add different battery icons into your model, and each icon would represent a different type of battery or different model. And then you can let Xendee decide, which is going to be the best one for your project.
Yeah. And to add to this, flow batteries can be explicitly modeled, but not in this view. It's in the expert mode. And I think I mentioned this on Monday. There are different views into the system. On this most user-friendly mode, we have the most used technologies. So, and that's, if you're missing a technology, in this view, there's a good chance that it's available in the expert mode, which everyone who gets a license can access. Or if it's really important from a business perspective, we can also think about bringing other technologies up. So I just mentioned flow batteries because they are a little bit different than regular batteries because they can be designed in terms of stacks, which is the power, and in terms of tanks, which is the energy content.
Okay, now let's go ahead and just run an optimization so we can go through the full report once together. So For this one, I'm just going to ask Xendee to run me a reduced cost optimization. So Xendee is going to find me the best, cheapest solution, as well as dispatch. So for here, I'm going to choose reduce cost as my optimization decision. But of course, if you rather reduce CO2 emissions or have resilience requirements, which we'll come back to actually, we can do that as well. For the reference model, I'm going to select Xendee Computed. And what this means is that Xendee is also going to calculate your base case / reference case based on your existing assets as well as the utility. Now, remember, the only existing asset I have is my electric chiller. So in this case, my reference is going to be buying from the utility and using my electric chiller. And so in effect, when we consider our new investment scenario, which is all the new DERs I've proposed, that's what we're going to compare against. We have a lot of advanced analysis configurations. We're not going to go through them today, but we also have additional documentation as well as tutorials on all of these different analysis configurations if you would like to learn more. Now, I'm going to, oh wait, I completely missed a step. So let me go back to my optimization screen. So one other thing we have to do is actually enable power flow. Because if you don't enable it, Xendee is actually just going to ignore all the power flow components that we set. So what this is going to do is you have several options here. So first, you can limit your voltage. So Xendee will check if at any point your model is going to violate your voltage constraints. You also have two toggles. So the first is consider losses. So should Xendee calculate the losses as well as optimize around your system losses? By optimize around system losses, I mean optimizing your DER capacities so that you consider for losses. Because if you're optimizing for DERs and you're ignoring losses, you might come up with a solution. You might come up with like 1 megawatt battery. But now if you're considering system losses, you might actually need more generation. So you might actually need bigger capacities. So that's what this toggle is for. The next thing is consider branch capacity. And what this is going to do is Xendee is now going to enforce the capacity limits of your cables and transformers. Now, remember, I have set up my cables with appropriate power flow inputs, like ampacity and the rating. Now, if I turn on this toggle, Xendee is now going to enforce that limit. So if my connections do not have enough capacity, then that's going to give me an infeasibility. And this is the same thing for transformers. If I had defined a transformer that's going to be way too small and I enforce the branch capacity, then that's going to give me an infeasible solution. Now, once you have that ready, you can go ahead and run an optimization. Now, one thing to note with both multi-node modeling as well as when you enable power flow is that the optimization is going to take a little bit longer, especially the more complicated your model is, or you have more DERs, or you have more constraints. So it can actually take up to several minutes, whereas for single node models, which is what we did on Monday, most optimizations will finish within like 20-30 seconds. So instead of waiting for the optimization to run, I'm actually going to...
Maybe we want to also answer one of the questions. Should the DRs and other components at critical locations be used for loss considerations? I mean, you can add to this, but I mean, in terms of the locations, I mean, the exact locations determines the length between certain nodes. So yes, I mean, if you have the exact locations, then we can calculate the exact length, which will determine the losses. And as Rita was showing, you can also adapt where the lines are so that they can go around buildings. So, I mean, if you want to have accurate losses and you have a lot of power in the system that goes through this, I mean, it might be good to have somehow the accurate locations. But at the same time, I mean, don't forget, this is the first step. See, this is the last step in an economic analysis and the first step in a powerful analysis. And you might go into one line diagram anyway to do a more detailed analysis. But yeah, maybe Rita, maybe you have more to add to this. But
so I'm actually now going to switch to a pre-completed result, just so we don't have to wait for the optimization to run. But it's a exact same model. I'm just going to show you a result I already ran. So now we'll go through the report. If you missed Monday's session, I'll also just briefly go through the main parts of the report. So at the top here, you'll see the information on our project. And this is what Michael was saying earlier, is that there's going to be a lot of equations that Xendee internally runs through. And that's what it's doing when it's optimizing for you. So we have over 2 million equations in this project. So you can imagine it's going to be really hard to do, or basically impossible to achieve the same thing in like spreadsheets or like Excel. So at the top here, you're always going to see what we call like a summary table of both your costs and emissions. So remember, our reference case is our utility purchases as well as our existing chiller. And this is our reference system costs when we consider cost of utility, cost of running the electric chiller. And I didn't show this, but I did set up my electricity tariff for this specific location and site. So that's how Xendee knows how much it is to buy your electricity. For the investment scenario, this is going to be our new scenario. So including what I propose to be new DERs. And you'll see here, we're saving a lot of money. Compared to the reference, we're getting about 31.3% in savings as far as costs, but we're actually not saving. In fact, we're creating more emissions, and we'll see in a little bit why. But on the right-hand side here, you'll see this is what Xendee has solved or optimized for us to be the optimal mix of DERs to install. So it's basically chosen everything that I've proposed. So solar, battery, generators, as well as an absorption chiller. This table here, it will show some kind of key or common financial metrics that usually your bankers or financiers or project reviewers are going to be interested in. Now, if you scroll down, you'll see we have a lot of different tabs. The summary tab is going to have just some basic overview of exactly where your values or savings are going to look like. This is really just more of an overview. We'll get deeper into the report. Now, before I go farther, when you get your trial account, I really recommend and encourage you to actually go through the report on your own and make sure that you like digest and understand every part, because the report is really one of the most important parts, because that's how you understand where you're getting your savings from. The financial data tab is going to have several key charts as to how your microgrid cost break down, your ROI, your cash accrued, and it's going to have two very detailed cash flow tables. So one is going to be what we call the cost cash flow table. In this table, it's going to break down by line item the cost for your microgrid, running your microgrid. So you'll see we have a line for utility demand charges, electricity charges, fuel, OPEX, all of the CapEx for all of my DERs, as well as the connections, so the cables and transformers, any incentives, as well as replacement costs based on our project lifetime. And you're also going to get a savings cash flow table. Contrary to the cash flow cost table, the savings is going to show you the savings that your system produces relative to the reference. So this one is very important. It's relative to your reference. Remember, our reference is our utility and electric chiller only. So this is in fact saying that now with the new proposed system, so all of my new DERs, I'm going to save, 200,000 in terms of demand charges for utility. I'm going to save this much in terms of electric utility purchases. And now you'll see we now have negative savings for fuel costs and DER maintenance costs because we didn't have those costs before. We didn't have any fuel fire technologies before, and we didn't have as many DERs before. Again, if you keep scrolling down, you'll see the same line items except for savings perspective. And then you'll see this is also how you'll see how your project breaks even and turns positive. So the cash flow table is very important because it breaks down exactly your microgrid costs and savings, but by all the different line items. So it's important that you make sure everything makes sense there. The next tab is our simulated utility data tab. Again, this is going to be based on the utility tariff information that you've input in this model, which I've skipped over for this part because that was in the fundamentals session. But just know that all of this is going to be based on the utility tariff that you put in or have set up. But now you'll see here, basically the main takeaway from this tab is that we're saving a lot in terms of utility charges with our DERs. The next tab is energy balance and technology investments, which is just going to have a lot of good pie charts that break down your electricity as well as different types of energy demand balances, like how much you're buying from the utility, how much you're producing on site. So basically a lot of pie charts that you can use in your report. The next tab is called balance of systems, and this is specific to a multi-node power flow model. If you're familiar with single node or you watch Monday session, this tab is not in a single node model because we didn't include any connections. So this is essentially like a bill of materials for your network. And now remember earlier, I had done a few different things to set up my connections. So I had defined my own cable. But remember for the transformers, I had actually used Xendee sizing, which is a functionality that lets Xendee pick out an appropriate transformer from the catalog. So this is actually now where you can see which transformers Xendee has selected. And remember that we had 3 transformers. All of them had different basically capacities at the secondary side. So you'll see that all of them have different transformers because we don't need the same size transformer for every connection. You'll also see we have cooling pipe in here, as well as its costs. The next tab is dispatch tab, which is going to be in every single Xendee report, regardless of single node or multi-node. And this is basically where Xendee spits out for you the ideal dispatch. And this is what you can then apply to your controller. So let's first look at the electricity dispatch because we have a few dispatches here. You can browse by different months, as well as date types, as well as the node, because remember, we have a lot of nodes. So let's just look at the aggregate view overall and what's going on. So this black line here is going to be basically our overall electricity load, so how much electricity we need. The dark blue bars is going to be our utility purchases. So now you'll see we actually have not that much utility purchases. We're going to be relying mostly on DERs. The yellow bars is our solar PV that we've installed. So it makes sense that it's only during the day and it peaks midday because it's solar. The light blue bars are going to be our CHP generators. So we're going to be relying on a lot of generators for electrical consumption. This dark green bar here, or olive green bar here, is going to be our battery. So we're actually using, in this case, the battery for some peak shaving. So the battery state of charge is going to be reflected by this pink line here. So you'll see in the early hours, the pink line or the state of charge will go to basically 100. So that's when we're charging the battery. Here's also when the utility is cheap. And then kind of in the peak hours, the battery will discharge. And then in the late night again, it'll recharge when the utility rates is cheap again. Again, I didn't show it, but our utility rates, I've set that up separately, and it is time of use. So that's how the battery knows when to buy and when to discharge. Now let's go over to the next dispatches. We have a heating dispatch just because remember our generator is a CHP combined heat and power unit that basically makes waste heat. So that's why it says heat from distributed generation. That's our waste heat. And in turn, that waste heat is going to be used for our cooling with our absorption chiller. So now that you'll see our absorption chiller, this like light blue, is now meeting all of our cooling instead of using our electric chiller. The next tab is, oh, sorry, let me go back to the dispatch again because I want to show the different nodes. So this is the aggregate view, basically what you would see as like a bird's eye view. Now, if you go to your different nodes, so say, for example, looking at my admin feeder, which remember is just like my little admin slash office, you'll see it'll reflect the demand of that specific load as well as where it's getting its energy from. In this case, it's saying energy imported from our switchgear because remember that's the previous connection that's getting the utility electricity. If we go to our cooling, for example, we don't have any load because remember that's our cooling stack. If we go to our server hall feeder, which is where all of our racks are going to be, you'll now see the load reflects that of the server hall, which is, about 10 megawatts. And the energy is going to be shown to be imported from the UPS because, again, that's the previous connection that gets utility power or power from our switchgear. Now, if we go to our switchgear, which remember is where all of our DERs are connected in this case, so our generator and solar, you're going to see this is where you can see their generation. Again, with some energy imported from utility. If you go to our uninterruptible power supply, this is where our battery lives. So now you'll see the generation as well as state of charge for the battery. Okay, let's move on to the power flow tab, which again, this tab only shows up if you run a multi-node model with power flow enabled. And what this tab is going to have, it's going to have a few sections of information. First, relating to your network voltages. Remember, I have set voltage constraints for my site. So it's going to make sure and report the voltage that each node is running at. So as you can see here, all of our minimum and maximum voltage are within the constraints I set. So just from this preliminary modeling, doesn't look like we have any voltage sags or rises. But of course, that's probably something you want to later confirm with like a detailed power flow modeling. We'll also get a table with network losses based on the power flow losses and power flow specs that we set. If you scroll down, you'll see some time series plots for voltage, active power, and reactive power. Similar to the dispatch, you can view this by the different months, day types, as well as the node. So let's just take a look at the overall aggregate view first. So the voltage is pretty consistent. If you hover over the points, you can actually see the numbers. So active power, there's a lot going on here. So we'll basically see the active power from all of our DERs, as well as you'll see negative numbers in the actual like pop-up, but this chart goes from 0. So it's a little bit hard to read, but you'll see that there's going to be negative power at different nodes if it's going to be importing from a different node. Reactive power, you'll see, again, we have the actual numbers when you hover over the chart. So let's look at this at an actual specific node. So let's look at, say, the switch gear, which again, the voltage is pretty consistent. For this one, the active power is going to be all positive because it has active power from the generator as well as the solar. For the reactive power, I think it's just going to have reactive power from the generator, not the solar. The last tab is just operation summaries. So it's just some helpful summary charts about, how much your technologies were used, how much they generated, how much they were ran, as well as emission summary. The last tab is our print report tab. This is where you can print out your report into a digestible PDF form, which you can then, use for your proposal or like put in your report. You do have the option to customize which reports or charts you want in your PDF because you might not need every single chart in there. Okay, we have about 30 minutes. Michael, do you want me to open up quickly one line?
Yeah. So I have this suggestion. I mean, I would, in your case, as you said, open up the online so that people can see the process. And then it has been a very long day for most of the people here in attendees. So if we can, I mean, we can answer questions after this. But then, if they're not really pressuring issues in terms of questions, we can close this earlier. So I would suggest showing the online, and let's see if people have very specific questions or challenges. Then we answer this, and then I think we can close this for the day.
Yeah. Okay. So remember earlier we were presenting in the slide deck that you can transition this directly from a multi-node techno-economic model to a one-line project. So you would do that here. You see this button that says open as one line. And what this is going to do is it's going to take the results from this optimization and directly change it into one line. You can choose your format as well as units. And once I create one line, it's going to create a one-line version, but it's also going to save your original multi-node model. So you can always go back to that and make changes if you like. So what you'll see here is a one-line or single-line diagram. It's going to have basically all of our nodes as well as DERs on here. So this is a utility right here. We have our transformer, all of our DERs. We have 10 generators, so that's why they're all here. If you scroll over, you'll see our solar, battery, and then our loads here. Michael, is there anything else you want to add about one line?
No, I think I don't want to extend it too much because it's already a lot. So I think we conclude this with this and answer some questions. And if they're not really pressuring questions, then we can conclude this. I was just going to answer a question from Jonathan. I think I will just say it here. I mean, if my absorption shell takes hot water, do I include any hot water losses as part of the COP or loss coefficient? I mean, that's one way of doing it. If you would send it through pipes, then of course, in the pipes, you can also model losses. But these things can be modeled, and there's certain ways of doing this. And this is a good question, for example, to reach out to Rita if you start modeling this. Okay. There's a question which has been hanging around there for a while, and maybe Rita, you want to answer the first one. You might know this better than I, from Edward.
Okay. The answer is, can the various types of tax savings be broken out to show compliance or taken benefits from having a microgrid?
I mean, we have certain tax benefits like tax credits and MACRs, and they will be reported. So, I mean, maybe you want to go back, read to some of the results where we show macros and tax incentives, and maybe that's in another project. I think we didn't do it here. Maybe from the single node.
I might have some input,
Yeah.
but
So this is what we're doing. So if you're asking if we can break this further down, I mean, we could change that, but that's what we have here with ITCs, macros, and all that stuff is basically
yeah.
shown here.
But there's more incentives. I've only shown that this specific report only shows macros and incentives, but that's just what I have set up. But we have other
That's a good point.
incentives.
Maybe you want to go to the incentives because there's way more to this.
Yeah. But yeah, you'll see we have different incentives types or like revenue streams. You can model demand response, which is we have a whole other tutorial on this. Grant funding that you can apply to different DERs or like your whole project. A few other ones are going to be mostly specific to the US. But yes, you have the option to kind of break that down further to show your savings. And
Yeah.
you might also, if you're really trying to like model different versions with different tax incentives or compliance, and this is where you might want to do scenario analysis and run different
Yeah.
models with different incentives, different,
Yeah.
findings
So
as well.
there's another question regarding net metering, and it's actually not an incentive. It's coming in through the tariff,
Mhm.
and maybe you just want to show this again, reader. So if you bring in a tariff through an API, then you
Yeah.
can select the different net metering tariffs, and they're coming in automatically, NEM3, NEM2, whatever it is. So yeah, it's done, and maybe. I'm not sure at this location if there's net metering, but maybe you want
I
to show
actually
them.
don't think this one has. Let me pull in one that does projects. This one must have. Yeah, so it depends on your tariff. And for most people, if you're in the US or North America, we actually have Genability integrated. Genability is a third-party company, and their job is to maintain North American tariffs and update them regularly. And depending on your project location, that's how Genability knows which load serving entity as well as tariffs are applicable to your site. So I pulled up a different project here. That's why it says San Diego Gas and Electric. Now, depending on your utility, you might not have this many options, but you can see San Diego Gas and Electric has NEM version tariffs, NEM 1, 2, and 3. It also has all the historical versions. So if you pull in a NEM3 tariff, that's how you would get the NEM3 structure set up. Let me just go through this. But we've actually specifically made a different functionality to be able to kind of break down all of the different NEM3 charges, which you'll see in a little bit. So now for NEM3, you'll see that supply, delivery, as well as other, which could be like, I don't know, transmission. It's all broken out. But since I've directly imported this from Genability, it's already filled in all of the charges for me based on the tariff I've selected, as well as the version I've selected. So yes, you can directly model NEM3 tariffs. Michael, maybe you want to take this next question.
Yeah, I was trying to type it, but again, of course, I forgot it about it. That maybe we should answer this live. So the question was if this is all Xendee design or operate. And if you recall, Adib was introducing this on Monday that we have these different products. This is all Xendee design. This is even not operate. So operate comes after the design phase, and we can move these design projects into operate and then set up the controller and start controlling the technologies if we also establish communication. So this is still all design and not operate. Okay. Okay. So Massachusetts and its utilities have a complex array of tariffs, incentives, and off-taking options. Can Xendee optimize financial structures for these variables? So I'm not the expert on this. I mean, I know that we modeled projects in Massachusetts. I'm not sure if you know about these details, Rita, but I mean, if you remember correctly, there's REX, if they're still there, which we have. We're also working with other entities like NIPE on the East Coast in New York to consider these tariffs. So my answer is I'm not fully sure to which of these incentives you're referring to. Some will be modeled, some can be modeled by certain tweaks of the expert mode, and we have projects around this. So Vince, if you want to get more details, I think I have to put you in contact with the engineers who have done these projects in the past.
Yeah, it really depends on what specific incentives or off-taking options you're talking about, because we have model projects in Massachusetts that are enrolled in like demand response or that type of programs. There's two main ones in Massachusetts. I already forgot their names, but they are doable. So yeah, it just depends on what programs you're talking about.
Yeah. So another question is, does the microgrid controller icon in this model have any functionality then to be a fixed cost? Yeah, I mean, this is just for costs because the controller itself is mimicked in the optimization itself. So what Rita was showing when she was showing the dispatch, this is actually the output of the controller, and we implicitly calculate the smart controller. This icon is really what are the costs, how do you want to consider installation costs or operation costs. So it's really costly.
Mm-hmm.
Okay, I think we have exhausted all the questions and answers here. And I think it's okay if we end a little bit early, because I think it was a very extensive day for everyone if you were participating also the other session. So I think we all deserve an early break here and ending by 50 minutes. Tomorrow, we will have another training session, which is around financing. And there will be also a couple of interesting use cases presented, I think, by universities in the morning. And then, of course, there's a Department of Energy and Department of Defense session. We'll talk a little bit about the controllers there. And there's a very specific one also regarding controllers later tomorrow. And if you're interested in Operate, I will talk a little bit about this. And then also Adib Nazli, our CEO, will host that panel with other industry partners. So with this, thanks everyone for really powering through this day and doing all this, and seeing you tomorrow. Thank you.
Thanks, everyone.